Exercise 8.7 returns to the two neighbors of exercise 8.4. And we need to continue to assume that neighbors I's average benefit per hour of work is equal to this expression over here. It's the same as in 8.4. And we need to continue to suppose that player 2's opportunity cost of an hour of work of landscaping is 4. The thing that changes is neighbor 1's opportunity cost, which can be either 3 or 5 with probability 1/2. And this cost is neighbor 1's private information. So neighbor 1 knows which type he is, marginal cost equal to 5 or marginal cost equal to 3, but neighbor 2 does not have this information. So this is the perfect setup to solve for a Bayesian-Nash equilibrium, and that is what we will do in 1. We need to indicate it also on a best response diagram, just like we did in 8.4. And then finally we need to address the question, okay, suppose that player 1 knows the type. If he is low marginal cost or high marginal cost, which of the two player 1 types would like to send this information to player 2? Okay, so let's start with exercise A, solve for the Bayesian-Nash equilibrium. And the situation is as follows. The opportunity cost of player 1 is 3 with probability 1/2 and 5 also with probability 1/2. And the probability is really from the perspective of neighbor 2, because neighbor 1 knows what type he is, but neighbor 2 doesn't know his neighbor that well. So he needs to make an assessment. Player 1 knows the opportunity cost, his type, player 2 doesn't know it. And if player 1 is of the low cost, then the best response of player 1 to the actions of neighbor 2 is 3.5 plus L2 divided by 4. So you can return to your notes to exercise 8.4, where you also need to derive the best response functions. Well, if you know if you know the cost of your opponent, you know that the cost of your opponent is equal to 4. You know that your own marginal cost is constant and low at a level of 3. Then your best response function to what the other neighbor does is 3.5 plus L2 divided by 4. If your marginal cost is higher, if you're of the high cost type, so your opportunity cost is equal to 5, then whatever the neighbor does, it's less attractive for you to work on landscaping. So you will provide less effort for any effort level paid by the neighbor. So if you're of the high cost type, you start out with a base level of 2.5 instead of 3.5, and your effort is increasing 1/4 of the effort level of the neighbor. And player 1 again knows which type he is, so he knows his best response function, but neighbor 2 does not know which is the actual best response function of neighbor 1. So for player 2, he will play against neighbor 1, but not knowing his type, he will choose his best response as if he would play against the average of the neighbor 1. So his best response is he makes an assessment about what player 1 will do. Well, the expected action or the average action is the action that player 1 will choose if he's of the low type, which happens with probability 1/2, and when he's of the high type. And the L1 bar is really defined as the average of the low cost and the high cost effort that the neighbor will make. So it is as if, okay, you live in a home, but you don't know whether your neighbor is really of the type that's at home a lot and will pay a lot of effort in the garden, or is not at home a lot. And you cannot wait to see what type the neighbor really is. In real life you might find out after some time. In this exercise you don't have the opportunity, you just need to choose your effort level yourself making an assessment of the expected type of the neighbor. And then the best you can do is to take the average of what a low cost and the high cost neighbor would do. And once you know this, then you can replace the L1 bar by this expression, and then you can also replace the LC and high C or LC and HC best response function by the expressions over here. We do that in the next step. So the average best response of the neighbor 1 is the average of this best response and the average of this best response. So it's identical to 3 plus L2 over 4, because 3 is the average of 2.5 and 3.5, and the average of L2 over 4 and L2 over 4 is L2 over 4. So now we can replace the L1 bar in this expression by this expression over here in order to arrive at this best response function for player number 2. And then we simplify a little bit, and we get 15 over 4 plus L2 divided by 16. Again, we solve for L2, bringing this to the left-hand side of the equation, giving us 15 over 16 times L2 is equal to 15 over 4. So neighbor 2 will spend 4 hours of effort. And in fact, this is the same as in exercise 8.4, where we also found equilibrium effort levels of 4. And this is, in this case, just because the average best response function of the low cost and the high cost neighbor, if you weigh them with a probability of 1/2 each, is exactly identical to the thing that we had before in exercise 8.4. So it's a little bit by coincidence. If you would take the weights other than 1/2, you would also get a different outcome level than 4 over here. But okay, given these probabilities and the possible cost types of the neighbor, neighbor 2 in equilibrium will make an effort level of 4, and neighbor 1 knows that neighbor 2 will do this. So if he's of the low cost type, he will spend an effort level of 4 divided by 4 is 3.5 plus 1 is 4.5, and so this is a mistake over here. Well, really repair it again on the fly. So it is clear if you yourself are the low cost neighbor, then you're willing to spend more effort given any effort level that the neighbor supplies. So in this case, neighbor 2 will supply 4 hours of work. So if you're low cost, your opportunity cost is not that high, then you will spend 4.5 hours. If you have a high opportunity cost, despite the 4 hours spent by the neighbor, you will spend 3.5 hours in total. So that completes exercise A, and it's important that neighbor 2 will choose this one unambiguous effort level, and for neighbor 1 who can condition on a type because he knows which type he is, low cost or high cost. If he's low cost, he will spend 4.5 hours. If he's high cost, he will spend 3.5 hours. Then indicate the basic Nash equilibrium on a best response function diagram. Now, this is the best response function diagram, and the important thing to note here is that neighbor 1, he knows which type he is, so he also knows which is his best response function. If his opportunity cost is low, then this will be neighbor 1's best response function. If his opportunity cost is high, then he will know that this is his best response function. The issue for neighbor 2 is that neighbor 2 doesn't know exactly whether neighbor 1 is of the low cost type or the high cost type. So neighbor 2 will take the average BIS response function, so that's the dotted line over here, and then we'll play the action that corresponds to the action that he would play when he would face this average best response function. So what we have here is that neighbor 2 will always put in 4 hours. That's the vertical line that's denoted here. And then neighbor 1 will choose the high effort level of 4.5 if he's of the low cost type. And if he's of the high cost type, then he will respond to this effort level of 4 by supplying 3.5 hours himself. So that's question A in a diagram. And then we can finally conclude with question C. Which type of player 1 would like to send a truthful signal to player 2 if it could? And which type would like to hide the private information? Well, if you look at the graph, what you can see is that if you leave neighbor 2 in the dark, then neighbor 2 will just make an assessment of the average best response by neighbor 1. So he will make an assessment that on average the best response will look like this. And he will act accordingly and spend 4 hours of work on the garden. But now, if this neighbor 2 would know that his neighbor has a lot of time, that his opportunity cost is low, such that the best response function is actually this line over here, then neighbor 2 would also spend a higher amount of effort himself. So if you know that your neighbor spends a lot of time on the garden, then you also want to spend somewhat more. Whereas if you know that the neighbor has the high opportunity cost, then you know that this is the best response function of neighbor 1, and you as neighbor 2 will also reduce your effort level. So long story short, if you are of the low cost type, saying, okay, I don't have a lot of opportunity cost, then you want to reveal this information to your neighbor, because we already told in exercise 8.4 that the effort levels are complement. The marginal benefits of spending time in your garden is increasing with the number of hours that the neighbor spends. So if you can truthfully reveal, I have low opportunity cost, I will spend a lot of time in the garden, then the neighbor will also spend more time in the garden, increasing your benefits as well. So that's the intuition. Now in terms of formulas, so if you have the low cost, if you are of the low cost type, then your objective function is the benefits of gardening minus the cost of gardening, where the opportunity cost of 1 hour of gardening is equal to 3, because you're of the low cost type. And your Bayesian-Nash payoff is equal to 4.5. You will spend 4.5 hours in the garden. If you don't reveal this information to your neighbor, then the neighbor 2 will play against the average best response. So it will supply an effort level of 4, as we found in question A. So these are your total benefits, and the total cost is, your cost per hour is 3, or the low cost type, and your number of hours is 4.5, and your total payoff is equal to 2025. Now, if you could reveal truthfully to your neighbor that you have low opportunity cost, so you give full information, in that case we are back to problem 8.4, because neighbor 2 will respond to your effort level of neighbor 1, and that will be 3 times L1 over 4, and you yourself are the low cost type, so your best response function is 3.5 plus L2 over 4, and that's what we observed here in question A. So now we can solve this system of 2 best response functions by inserting this expression, the second one, into the first, replacing the L1 over here. And if you do so you plug this in, then you can simplify. So and you get that L2 is equal to 62 over 15, which is 4 to 15. And if you plug this number into the expression for L1, like the one over here, then you get that L1 is equal to 8 over 15. So now in equilibrium, you are the low cost type, so you will spend in equilibrium 8 over 15 hours in the garden, which is more than the 4 that you spent in exercise 8.4. And also because, well, you truthfully reveal to your neighbor that you're of the low cost type and you will spend some time in the garden, your neighbor will also spend more than the 4 hours that he spent initially. So plugging this into the objective function of the low cost type neighbor, then you find that the Bayesian-Nash payoff of this neighbor will be equal to 20.25, which is more than the 20.25 if you don't reveal your type to your neighbor. So in conclusion, the low cost neighbor would like to reveal his type to the other neighbor. And if you're of the high cost type, if you know that you don't have a lot of time, you want to hide it, because if you would reveal it, it would only induce your neighbor to spend also less time on the garden, reducing your total benefits. And that completes exercise 8.7.